there's one thing I wanted to touch on. So recall, what did we do last time? There's an interesting question. So we started with pre-measure. We extended it to an exterior measure. We restricted that using the Carathéodory measurability criterion to a measure and to a sigma algebra of measurable, bless you, Carathéodory measurable sets. And then the actual Lebesgue measure was the restriction of the exterior measure to this. Okay? So the question of uniqueness, right there, thanks. So the question of uniqueness, so uniqueness, when we had this uniqueness discussion, I'm just thinking about this, I hope I can come up with an argument. The uniqueness said the following. We have this non-sigma algebra, we have an algebra, A. We extend it to the power set of X. That's where mu star is defined on. We restrict it using this definition, which is a human definition. This is a human definition, right? We had several versions of it. The first version, when we did Lebesgue's actual version, was open sets covering the set with the exterior measure at most epsilon for any epsilon. And then we had this new version, which was that it decomposes any set into a set whose exterior measure adds appropriately, is additive across that set. So here's our mu. And the question was, well, could there be some other sigma algebra which supports, so I called it B for the Borel sigma algebra, could there be some other sigma algebra which supports a measure, meaning countably additive, not countably subadditive, countably additive measure? So uniqueness, could there be another beta nu, so x beta nu, with nu equals mu star restricted to beta?
And are you saying it's incomparable with?
Yes. That's not compatible with beta, and I claim that can't be. So claim, or I guess I should call this a theorem, claim beta actually must be contained inside. Yeah. So M is the biggest you could possibly do. So what we proved last time was on the intersection of B and M, nu agrees with mu. And now what I'm saying is, if nu is any extension of mu star, then anything that's any measure, anything that's a measure that's a restriction of mu star, is a measure whose sigma algebra is contained inside the Lebesgue, the Carathéodory sigma algebra. Okay? All right. So let me try to give you an argument for this. Let's see if you like it. This was an added discussion.
So the claim is if nu restricts mu star, or if nu extends mu zero?
If nu extends mu zero by restricting mu star. Okay? So I am going to take mu star as kind of like the mother exterior algebra from mu zero. Again, you could say, well, couldn't there have been some other definition of mu star? Isn't there some other exterior measure that extends mu zero? We can have that discussion another time. But this definition is pretty natural. Whereas the Carathéodory definition, we really have to think about. Why is this the right definition? Why is it a universal definition? Right? Where's the kind of universality of it? So this is my claim of universality. Okay. So let me make two claims, two facts. Let's just make them facts or exercises so that we don't spend too much time on them, because I actually want to get to other things, but you asked an interesting question, so I wanted to address it. So fact one is that when you compute this exterior measure, right, the definition of exterior measure is take covers which are countable unions of things in F, but in fact, things in A. A is our pre-measure. In fact, you could take things that are in A sigma, A delta. Delta is the intersections. So this is the all intersections, countable intersections of things in A, and then just measure those. So my claim is that the exterior measure of an arbitrary set, which would be, you do this with the pre-measure here and the sum over all countable covers, you can do, I claim, just using A sigma, the analog of F sigma. The intersections, it's like the intersections of open sets are enough to measure the exterior measure. Okay, let me leave that as an exercise. Fact 2, this is fact 1. Fact 2 is that E is measurable, a set is measurable, if and only if, let's write it like this first, for every epsilon, there exists some F in A sigma with exterior measure of this difference at most epsilon. Which, by the way, is equivalent to, the real statement would be that there exists some F in A sigma with exterior measure and hence measure equal to 0. So usually you need an epsilon of room, but if you have these F's for every epsilon, then you have one for every 1 over n. And their intersection is a countable intersection of countable intersections, which is a countable intersection. So you can get all the way down to measure 0. Okay. So in one direction, this is clear. Yes?
We're talking about measurable. It is Cartesiodori measurable.
Cartesiodori. This M is always Cartesiodori measurable. Yeah. Thank you. There exists an F containing E. Thank you. There exists an F containing E with this set difference at most epsilon. Okay? So it's kind of clear in both directions. In one direction, well, there's a variety of ways of doing it, but for one example, well, we can use this equivalent definition. So, well, I was going to leave it as an exercise, but now I'm giving you the proof. F is equal to E plus F take away E. And F is measurable, and F take away E has measure 0, so it's measurable. That makes E measurable. In the other direction, let me leave it as an exercise. Both of these things are pretty simple. In the other direction, it's this definition of infimum that measures, if E is measurable, then its measure is equal to this infimum. And that's what this argument is saying. All right. So with these two facts, I can now prove the statement. So theorem, bless you, B is contained in M. Proof. If not, there exists some set E which is in B but not in M. If it's not measurable, if E is not Cartesiodori measurable, but it is whatever this other sigma algebra is, if E is not measurable, then this statement is false. Then there exists some epsilon positive, so that for all F containing E, F in A delta, the exterior measure of the difference is at least epsilon. Now E is in B, but nu of E, thank you. Yes, I should be reading my lines. So I'm going to use these two facts. I want to keep them there. There's fact 1. Okay, so E is nu measurable but not mu measurable. That means that no matter how hard I try, I won't find an F in A delta that covers it with less than epsilon overlap. But E is beta is B measurable, so its nu, which is also equal to mu star, is equal to this infimum. So, but nu is equal to mu star, and mu star is given by this infimum. That implies there exists some f in A delta containing E with mu star f, which by the way is mu and nu because both of them extend A, and this is in the sigma algebra generated by A. So there's a slightly bigger, let's see. In this picture is the sigma algebra generated by A, which has to sit inside both of these, since they're both sigma algebras containing A. So they're containing things generated by A. Okay. So I'm trying to say that mu and nu have to measure this, and they have to give it the same measure by the argument from last time. So so f is bigger than E, but it's only bigger than E by a little bit. By epsilon over 2, shall we say? I think this will work. So there is this epsilon. There is this epsilon. Now I'm going to fix that epsilon. Any element, any f which contains E and lies in A delta has this set difference at least epsilon. But what is the new measure of E? It's just mu star of E, which by definition of mu star, or by this fact about mu star, means there is some f which covers E and has mu star at most the size of E plus epsilon over 2. And of course, these are also equal to nu of f. And this is equal to nu of E again. But, a lot of buts here. Nu of f, nu is additive. It's a measure. So nu of f is equal to nu of E plus nu of f take away E. Nu of f take away E is at least epsilon. Nu of E is at least, so this is at least epsilon. This is at least nu of f minus epsilon over 2. Minus epsilon over 2. So when I add those two up, I get at least nu of f minus epsilon over 2 plus epsilon is plus epsilon over 2. So nu of f is bigger than nu of f plus a little bit. Okay? So there cannot be, this picture cannot be, B must sit inside M. In fact, all the books that I looked at just assume that B is equal to M. And they say if I had any other measure on the same sigma algebra. But it doesn't have to be the same sigma algebra. If you have any measure that's some restriction of mu star, it can't be another sigma algebra. So M is the right definition. This Carathéodory definition is the right definition. This is like a universality of the Carathéodory definition. Okay. So that was a very good question that raised this issue. And now we can get to Lebesgue integration. Any questions? Let's slide this up. Okay. What's going on? Now the top isn't good either? How did I do this before? Lights. Better? Let there be light? Okay, so Lebesgue integration. Lebesgue integration. So again, this is going to be general, so now we have some measure space is a measure space. Let's start with functions f from x to the positive or non-negative extended real numbers. So I mean 0 to infinity, possibly taking the value infinity. And whenever I write f, I always mean measurable. F is measurable. What does it mean in this general context? Same thing that it meant in the previous context, we know what open sets are in R. So the inverse of an open set should be measurable. Continuous would be the inverse of open set is open. I don't even have a notion of continuous right now. This doesn't have a topology. All I have is measure. Okay? So I don't even know what a continuous function is in this generality. All right. So that's what we're starting with. Now, a simple function, so this was f is measurable, is if this, f is simple, if the image, if the range of f is finite. Okay, so f only takes on finitely many values. How could f take on, so let's say this is finite, f of x is equal to some finite numbers, c1 through cn. This is a subset of the reals. Can you see this? Why is this getting worse?
I think the brightness is like,
Yes.
The brightness
The
is
light.
like it's too much.
that light?
Yes.
Oh, that light I can't do anything about without.
Are you playing break over? Is it really?
Unscrew some lights. All right.
More of this right
We'll get through it. We'll get through it. By the last lecture, we will have some perfect way of being able to preserve these things and you being able to see and video and so on. Okay, so if it takes on only finitely many values, well, let EJ be the pre-image under F of each of these CIs, CJs, I guess. This is a measurable set, because not only is this true for opens, it's true for complements of opens and closeds and whatnot. So this is measurable. So F is in fact equal to the sum as J goes from 1 to n. This was our previous definition of simple functions, just functions with finite range. Okay. Yeah, I guess I want, well, yeah, so the EJ could cover all of x. So I'm not saying that it has to have the value 0. One of these could be 0. But the EJ could also cover all of x. Or this includes the case when one of the values is 0 and then x take away all the EJs, the finitely many EJs is the rest of it. All right, so we're going to start with simple functions. Now, there's a problem with simple functions, which is exactly what we were just talking about. There's more than one way to express a simple function in these terms. So this representation is not unique. This is not unique. So we'll define a canonical term, a canonical form, definition, a canonical form for F is the set of, so again, the image of F is a finite number of distinct non-zero numbers, and possibly the value 0. Well, I don't want the value 0 as one of the CJs. We're going to make this canonical. So it's this exact expression. F is equal to a sum CJ chi of EJ. EJ is the pre-image, and there's now kind of no ambiguity about this. In other words, I can't write the function 0 as chi e minus chi e because, okay, I have C1 is equal to 1 and C2 is equal to negative 1. And I've expressed it as a simple function, but this is not the canonical expression. The canonical expression is, in this case, the empty set here, and the sum of the empty function is the 0 function. Question?
Does setting EJ equal to F inverse of CJ and CJ distinct ensure that you're going to get the canonical form?
Yes.
Those are the two things to make sure of.
Those are the two things to make sure of, yes. So in general, so I was saying two things. One is, if the image is finite, then f is expressible in this way. But any expression like this is a simple function. And what I want is the canonical version of it, which is the one that I just described. Okay, so given a simple function, let me take this away and slide it up. So given a simple function in canonical form, the definition, given a simple function, let's call it phi now, in canonical form, and for now we're doing everything non-negative, we will define the Lebesgue integral of phi with respect to mu in the obvious way. Some Cj chi measure of Ej as j goes from 1 to n. The first thing that would be nice to know is that this definition does not depend on the representation. We defined it using the canonical representation, but if you had any other representation of the same simple function, it should have the same integral. So that's a lemma. Definition is independent of representation, i.e., if phi, which was canonically, the integral is defined like this, but if it's also equal to some aj chi fj, now with no conditions on the aj being non-zero or independent or something, and j goes from 1 to m, and the fj don't have to be non-overlapping. Yeah, I should have said, and the ej's are distinct. Ej's are pairwise disjoint. So now the fj's can be not disjoint. The aj's don't have to be non-zero. They don't have to be non-equal. So if you have any other representation, the integral will still be the sum over the aj's mu of fj. So we could have said take any representation and define it to be this, but of course we want that to be well defined, and the lemma says yes, it is well defined. This is very simple. What do I want to say before that? I guess I can save that discussion. Okay. So, sorry, that is what I wanted to say. So the convention, now I might, one of the aj's might be 0, and one of these measures might be infinite. Okay, so convention throughout is that 0 times infinity is 0. Okay, so if you have the value infinity, but that happens on a measure 0 set, that product is 0. If you have 0 that happens on an infinite measure set, that product is 0.
What about stuff like the delta?
So the delta function is not a function. It's a distribution, and we're going to get to distributions, and you can integrate distributions, and you can approximate distributions by...
But in that case, 0 times infinity wouldn't be 0.
Well, you never literally are multiplying 0 by infinity when you deal with distributions.
In the limit.
Yes. Right. So in the limit, we have all kinds of things that can happen. But this representation allows for this thing to appear. And I want you to know what you do when you see this. It's 0. 0 times infinity, when in this context, is always 0. So the second take the value infinity on a set of measure 0, the integral will give 0 weight to that. It can take the value 0 on a set of infinite measure, the integral gives 0 weight to that. So when you're integrating, this is the convention. Question?
Is capital M finite?
Capital M is finite, yes. I still want some other representation of phi as a simple function. Okay? All right. By breaking up these fj's, so the proof is very simple. You have these fj's, right? So they don't have to be disjoint or anything, but there's still only finitely many of them. So you can break up fj's to disjoint ones, to disjoint, I don't know, gk's or something. Is that a bad name? hk's. Okay, so chop them up into pieces that are disjoint. So you start with these fj, and then you make out of them little pieces hj, but on those hj's, it takes only one value, but those values might be the same. It might take the value a1 here, and it might take the value a1 here. So I want to regroup them. Okay, it's the dumbest thing you could possibly think of. So you break up the hj's into disjoint ej's, and then you group for each value cj, let ej be the union over these hj's, where so each hj has a value aj that it came from, where the aj's are equal to the fixed cj. So it's a mouthful when you write it out, but it's obvious what's going on. You have finitely many sets. You break them up until they're disjoint. They might not have, I can't have more than one value of c representing anything. So for the finitely many values that this function takes, group them by those finitely many values. Question?
Can we use j's for all of these?
They're not all, yeah, okay, k's. Yeah, is that better? Again, notationally, it's a bit of a mess, but I hope it's very clear intuitively what's going on. So it takes some value. Let's say the value on each hk is some ak. If I really want to properly index this, it's going to be a nightmare. Let's make it a sub hk.
Okay. Yeah.
Each hk has some a value, which the function gives to that set. Okay? All right. So the point is, when you add all of these up, you'll get the same thing. Can you still see? I need to slide this up. So that was the original definition, and do I need to really say more about this? So if you sum, as j goes from 1 to m, of aj mu of fj, that's equal to, so each of the aj's happen, so that's the sum, each of the aj's takes some value, which is each combination of the aj's takes some value, which is a cj, and then times a sum over the cj equal to local sums of the aj's. God, how do I annotate this? Bless you. You see, the issue is, on some intersection, on this intersection of three f's, the value that it actually takes here is a1 plus a2 plus a3. So it's not the original aj's. So it's some sums of the aj's, ahk's, and then times the measure of these hk's. This is really bad to notate. Sometimes it is much easier to have a discussion. These were disjoint. These sets hk were disjoint, so their measure is equal to the measure of the ek, which is their union. So I guess here I also want to have a summation sign. Okay, so one more time. If I have some set where it takes the value 1 and some other set where it takes the value 2, well, on their sum, on this intersection, the function actually takes the value 3. So that's all I'm saying. Whatever those, break up the h's into disjoint bits, and then what is the value of f on that h? That's a fixed constant. It's not necessarily one of the aj's. It might be some combination, some linear combination, some sum, not linear, just sum of the aj's. That's the values of the cj that the function takes. Add them all back up.
You're just using the property of measure to make sure, you can just break it apart without.
And everything is finite and,
Yeah.
okay, good. This is like the hardest proof of the easiest theorem. But this has a lot of beautiful consequences. So corollary, so the fact that this definition doesn't depend on, we needed some way of defining it. Well, we could have defined it as take any decomposition and define it to be that sum. Then we would have to prove that it's independent of the definition. Instead, we chose the canonical representation, defined it in terms of the canonical representation, then proved that it doesn't depend on the representation. And now we have a lot of easy corollaries. If you have two simple functions and you add them, that's still a simple function. And the integral of that will be the sum of the integrals. Proof doesn't depend on the representation. So just add them, you get some some other representation for this which isn't canonical, but it still has the same integral. How about a constant multiple? Constant multiples pull through because they're just change all the AJs by a constant multiple. If E and F are disjoint, then the integral over E union F of a simple function is equal to the integral over E of the simple function plus the integral over F of the simple function. The integral over a region means times chi E, which is still a simple function.
Or E union F, but yeah.
E union F, thank you, in that case. Okay, so this is still simple. All right. And in fact, so let me put 5. Yeah, if phi is... What was 4? Ah, thank you, 4. 4. If phi1 is less than phi2, pointwise, then the integral of phi1 is less than the integral of phi2. Okay, again, you do this pointwise from the definition. Or the difference between phi2 and phi1 is a positive simple function, which is non-negative. So its integral is a sum of non-negative things. And 5, so if phi is complex valued, not just, we were talking about positive valued things, but actually you can extend the definition in the same way. If it's complex valued, then the integral of phi, extended in the obvious way, is at most, I just want the triangle inequality. Okay, and this is just a finite triangle inequality, so there's really nothing to do. Good. So those are all obvious corollaries. All right, now we're gonna, we know what to do for simple functions. Let's figure out what we're gonna do for general functions. We're gonna build up that theory. All right, let's recall. So there's a variety of ways of doing this. In fact, I actually don't like the way Stein-Shikarchi does this, surprisingly, since I like almost everything else they do. So let's just recall. I'll explain what they do and why I prefer the other way. Well, it's kind of the same thing. Do we want a canonical way of defining Lebesgue integral and then prove things about it, prove that it's independent of that representation, or do we want a general definition? So let's do it in the other direction. Since we did the simple function definition one way, let's do the general definition the other way. But I do want to recall that if f, so again, is from x to the extended non-negative numbers, is measurable, then there exists a sequence of increasing simple functions increasing up to f, and the proof, we only proved this in RD, but the proof is exactly the same. So you chop off at some finite height, whatever n was. Now I don't have a notion of balls of size n, but if you remember, that part of the argument was kind of irrelevant anyway. So you just truncate at height n, and then chop into pieces, and then each piece you straighten out the function. All of those are measurable sets. All of these EJs are measurable. EJ is measurable. And you make a simple function, and then you make sure to always bisect these things. So you take 2 to the k sets, and I'm just reminding you of the proof that makes these simple functions that increase and increase to f. Okay. So the Stein-Shikarchi definition of Lebesgue measure is you take one of these increasing sequences. Well, so definition 0, which is not my preferred definition, is that the integral of any non-negative function, by definition, is take one of these limits, is the limit of the phi k's, the integrals of the phi k's, which we know how to measure, that increase to f. let me give you my preferred definition, because somehow it's just two sides. It's two different ways of doing the same thing. A preferred definition, my preferred definition, doesn't have to be yours, obviously isn't Stein's, so I would say I'm usually the one that's wrong when that happens, but so be it. My preferred definition is that the integral of f is defined to be the sup over any simple function that's non-negative and at most f of the integral of phi d mu. I think this is actually easier to work with. It feels harder to work with because this is a massive space. Whereas this, okay, we have some nice, we constructed this sequence. This is very constructive. We constructed this sequence of phi k's very explicitly, and so we can compute its limit for any particular value of k, and then we take the limit as k goes to infinity, and that'll be the limit. Yes?
So then, like, for the soup, up to a certain extent, you have like a choice, right? And that makes it like easier to work with up to a certain extent.
I think so. I think read Stein-Shikharchi. You'll see they really have to work quite a bit harder to make this definition do what they want it to. It's a choice. The axiom of choice. All right. So right. One more thing I want to say: if this sup happens to not be infinite, then we say f is Lebesgue integrable, and we write that as f is in L1. And if I need to specify, it's L1 of mu or L1 of x d mu, some people write. There's a million different notations for the same thing.
What's the difference between mu and d mu?
Choice of, some people want to write integral phi of x mu of dx, which is really perverse if you ask me. But, I mean, these are all notations which mean exactly the same thing, and it's up to, you'll see in maybe older texts prefer this way of, because mu is a measure. You're supposed to measure sets. What set are you measuring? dx? dx is a set, or d mu, or what's the derivative of measure? Right, so some people prefer one way or the other. I'm just going to write d mu because that's, I think, what most people today write.
D mu, it shouldn't be. It's d and the element, a symbol of an element that belongs to that space.
So Newton would argue about what this symbol d means, and I will just say, here's a definition. I'm choosing this notation, but this notation should not be, this symbol d has no meaning. What has meaning is, what's the integral of a simple function? Take the sup over all simple functions. This is a massive space. Maybe you don't like it. Maybe you prefer to have something very constructive. Here's a constructive version, and we're going to prove that they're the same. But I'll take this as the definition and work forwards from it rather than the other way. It's like, do you want to write left to right or right to left? There are cultures that do both, and both are fine. Okay. All right. So the thing that's going to make this definition run very smoothly is the monotone convergence theorem. Okay, if I have a sequence of non-negative functions increasing, that's the monotonicity, and increasing to f, in other words, the limit pointwise, so this is pointwise, for every x, fn of x converges to f of x, could be infinite, f of x could be infinite, then the integral of f d mu is equal to the limit as n goes to infinity of these integrals. And I'm going to stop writing d mu. We don't have another measure floating around right now. When we get other measures floating around, then it'll be important to remember which mu we're integrating with respect to. Proof. Let me slide this up. You can see everything?
Yeah.
Do you need this upper part? Yes?
Can you replace the pointwise with almost everywhere?
We will in a minute.
Okay.
Okay? Slide this up. Okay, so right, the fn's are increasing. Fn of x are increasing. Increasing. So have a limit, possibly infinity. Just to explain what I mean there. What's clearly the integral over the fn's, each integral over the fn's is at most the integral over f. Again, because f minus fn is a non-negative function, whatever that integral is going to be non-negative. You're adding up non-negative things. So we need to prove the other, so hence it's true in the limit. Hence limit of fn's is at most the integral of f, need other direction. It's analysis, you prove an equality with two inequalities. All right, so let's fix, here's a little trick. Here's another epsilon of room trick. Fix some real number between 0 and 1. Okay. By definition of, let's just take any simple function. Let phi between 0 and f be any simple function. And then what I want to say is, and set, so I'm fixing this simple function first, and then I set En to be the set of values x and x for which fn of x is at least alpha times phi of x. So let's think about this. Okay, this is going to be like a triple limit. I'm going to take a limit as alpha goes to 1 at the very end. Then I'll take a limit over a lim sup over all phis, but just give me one. Phi lies between 0 and f. I want to look at the points in x. So for each n, I'm going to look at the points in x where fn of x is at least some number just less than alpha of phi. Okay, now phi is less than f. Alpha phi is strictly less than f. These numbers are increasing to f, possibly infinity. So what's happening to these sets as n increases?
It's increasing.
Or decreasing. No,
They're increasing. More and more x's
Yes, it's
are getting caught in this net. Okay? So these ENs increase all the way up to x. Because this is strictly less than f. And if these FNs are getting closer and closer to f, not in any uniform sense, just pointwise, this is pointwise increasing to f. Okay, the pointwise increasing theorem, and each En is of course measurable. Each En is measurable. That's clear. This is just some number, so this is a closed set, but anyway, it's a Borel set, so this is measurable. So here's our sequence of inequalities. The integral over Fn is at least the integral of Fn over the set En. So let's write that as times chi En. I mean, that's just because this is 0 or 1. This is always 1. I mean, the chi of x getting replaced by chi of En. Now, on En, when we're in En, this thing is at least alpha times phi. So this is at least the integral of alpha times phi on En. Nice little trick. Alpha is a constant, so that comes out. The ENs increase to x. So this increases, let me say it like this. Note that if phi is equal to some decomposition, not necessarily the canonical one, I need some new fj's, then phi times chi of En is the same aj chi of fj intersect en. And but this is still a finite list. And this capital N isn't going anywhere. Okay? So this integral the integral of phi chi en, that's just a sum of the aj's times the measure of fj intersect en. Just by definition of integral of a simple function. Now these measures, since the en's are increasing to x, these measures are increasing to mu of fj. If you have increasing sets, the measures, this is the monotonicity of measure that we proved weeks ago. Okay. So let's take the limit as n goes to infinity. So in the limit as n goes to infinity, we get that the limit of these integrals, is at least alpha times the limit of this integral, the limit of this integral. Each of these integrals is just this quantity, and it's a finite sum of constants going to this. So in the limit, this is exactly recovers the integral of phi. Question?
Can you explain why the intersection was at J?
So phi times chi en.
Right.
What is it? It's just aj times chi of phi j intersect en.
Right.
And so what's the integral? It's just aj times the measure of phi j intersect en.
Sure. But why does it increase to?
Why do the en's increase to x?
No. Why does the intersection increase to J?
Because the en's increase to x.
Sure.
So the fj's intersect the en's increase to fj.
Oh, okay, because FJs are strictly less than, right?
Fj's are whatever they are. En's are filling out all of space.
Right.
So the intersection of fj with the en's.
Right, but FJs may not necessarily, so you're just saying that in the intersection it would just be FJ. But the FJs could fill out the whole space.
They could fill out the whole space. Yeah. Yeah. This could be infinity. I don't know what it is. But the upwards monotonicity is independent of. I don't need like a condition like this. One of these measures is finite. If I have intersections of things, then I need one of them to be finite to know that the measure of the intersections converges to the measure in the limit.
But it may not fill the whole space, which is why you're making it FJ, right?
No, I'm making it fj because the sum of aj measure of fj's is the integral of phi.
Okay.
I want to argue that this limit is the integral of phi. Does that make sense? This is a subtle point. You're not convinced.
Well, I see why you want to do that.
No, but do you see the argument? So these are numbers, they're converging to this number because the sets are converging to this, are increasing to fj.
Okay.
So this is a finite list of numbers being multiplied by some non-negative constants. These points are increasing, so the whole thing is increasing to a sum of aj mu of fj. By definition, that is what the integral of phi is. Okay, this is the only subtlety. All right, this inequality is true for every phi, and so it's true for the sup of the phis. There's no phi on the other side. Okay, so the first was the limit as n goes to infinity, true for all phi at most f, so true for sup. In other words, the limit as n goes to infinity of the integral of the fn's is at least alpha times the sup of the integrals of the phis, where phis range over all simple functions at most f. But by definition, this is exactly the integral of f. The integral of f was defined to be the integral of phis over all simple phis at most f. And this is true for every alpha less than 1. It's true for all alpha less than 1. So send alpha to 1. You get the inequality in the other direction. So one more time. We're trying to prove that, let's slide it down a little bit. We're trying to prove that if you have functions increasing, and f is their limit, is that better? And f is their, we'll just call their limit f. That's measurable. The soup of measurable functions is measurable. Then the integral is the limit of the integrals. One direction is trivial. The other direction, you fix an alpha, you fix a phi, you make these ENs, the ENs increase. On each one, this is the key step. This is the key kind of cute analysis trick, which is used over and over and over again. You make a set on which something is true, and if you integrate on that set, that something is true. Okay, then in the limit, this goes to, in the limit, this thing goes to the integral of the phis. Now you take the soup over all phis, and finally you take alpha to 1. Okay, so let's look again at the statement of the theorem and compare it to the other definition. If you have any sequence of functions that's increasing to f, then this soup, this massive soup over this giant space, will catch the whole integral. Which means when you take the limit that we constructed, that one limit that we constructed, it will match the integral. Because all those functions are measurable, they're even simple. Okay? So that's why this definition 0, so thanks to the monotone convergence theorem, definition 0 is equivalent to the definition. Okay? All right. Let me just make a few obvious remarks. They're so obvious they need to be stated twice. So remarks. If you drop monotonicity, this fails in several spectacular ways. Dropping monotonicity fails in several ways. So, for example, if the FNs are, let's say the FNs are bounded, but maybe they're the indicators of x to xn plus 1. Okay, so the mass, so the integral of each one of these is 1, but that mass is going off to infinity. The limiting function is 0, but the limiting integral is 0, and each of these has integral 1. Okay? Another obvious example is Fn is equal to the chi, the indicator function of, let's say, 0 to 1 over n times n. This was on your quiz, right? Sorry? Your midterm, whatever. Some function where this, well, it's another example that could have been used, right? The point is each of these has infinite measure. Each of these has integral 1. The limiting function is 0. Let's make that. The limiting function is 0. It's 0 almost everywhere. Now it's 0 everywhere. But the mass is escaping infinite space, but in infinite, whatever you want to call this, domain, but it's escaping in range. So these are two kind of things that can happen. It can escape in range while being bounded. It can escape in domain. I mean it the other way around. This is escaping in domain while the range is bounded. This is keeping the domain bounded, but it's escaping in range. Okay, so the mass can escape in kind of, and these are basically the two counterexamples that you should always have in mind. Okay, so this is monotonicity failing and the conclusion failing. All right. Again, these are extremely obvious, and so they need to be stated several times. Okay. Corollary. Corollary of the monotonicity theorem. Maybe I should make this a separate theorem, but I won't. Corollary. Bless you. If you have this sequence of non-negative functions, then if you integrate the sum, that's the same as summing the integrals. If things are non-negative, then you can interchange summations and integrations. No other conditions needed. Okay, let's start with F1 and F2. Start with F1 and F2. So there exists some phi j simple functions that increase to F1, and there exist simple functions psi j that increase to F2. These are simple. By monotone convergence, the integral of F1 is the limit of these simple functions. And by monotone convergence, the integral of the psi j is the limit. The integral of F2 is the limit of the psi j integrals. So phi j plus psi j is also simple, is also increasing, is simple, increasing, and increasing to F1 plus F2. So by monotone convergence tells us that the integral of F1 plus F2 is the limit, as j goes to infinity, of the integral of phi j plus psi j. But each of these is simple. So inside this integral, I can break it up into a sum of two simple integrals. But this converges up to f. Again, by monotone. So I'm applying monotone convergence 3 times to get this extremely, like the linearity of the Lebesgue integral as defined over these soups. We're going to use monotone convergence 3 times to prove. So one order of monotone convergence is here, because these increase to these, so the integrals increase to the fj's, and they're simple. I'm not using that they're simple in monotone convergence. Here I'm using that they're simple. For each j, this is a simple function, which decomposes into these 2 simple functions. We prove for simple functions that the integral is linear. And now I'm using monotone convergence again on these, which increase to f1, and I'm using it again on these, which increase to f2. Question?
You can split up the limit over the sum because they're non-negative.
Now we're using real numbers. Yeah.
Real and
real
not
non-negative
going
numbers.
to-
Yes, real non-negative numbers. The sum of the limits is
We know the limits exist, so it doesn't matter.
well, they could be infinite.
Yeah.
It still doesn't matter.
Okay, yeah.
Okay. All right. So once you can do it for 2, you can do it for n. Once you can do it for 2, you can do it for n. So the sum from 1 to capital N of these fn's is equal to the sum from 1 to capital N of the integral of the fn's. Now the sum from 1 to n of little fn's I'll call capital Fn. And the capital Fn's are an increasing function, are an increasing sequence of functions, non-negative, to some other function, big F, where big F is the integral, is the sum from 1 to infinity, pointwise, of the little Fn's. So if I only had a theorem that tells me something about increasing functions, you see how many times we're applying this thing? It's like a, I don't know, some kind of hammer. Every problem after that looks like a nail. So by monotone, should we call this something? Monotone Convergence Theorem? MCT. I hate acronyms, but I also hate writing, so one of them is going to win. So what does monotone convergence theorem say? It says that the limit of the integrals of these fn's will be the integral of f. Let me put the integral of f on this side. But each one of these fn's, I mean, it's obvious, right? Each one of these fn's has integral, which is a sum from 1 to capital N. This is the limit of our capital N's of that. That, of course, is what it means to sum from 1 to infinity. And this is an integral of that infinite sum. Okay? Simple? Easy? All right. So that's what I mean by it's a corollary of the monotone convergence theorem. We just have it. We used it how many times in the process? Anyway, you can count. Any questions? Okay, let's get a few other trivial seeming, but they need to be proved, and they're not entirely trivial. They're worth proving. Things. If a function is non-negative, then its integral being 0 happens if and only if it's 0. Almost everywhere. Good. Okay? Proof. So if f is simple, then this statement is trivial. If f is simple, then what does this mean? It means a sum of the aj mu ej is equal to 0, which means any aj which is equivalent to any aj which has positive measure is equal to 0. Mu j has positive measure implies aj is equal to 0. In other words, f is 0 almost everywhere. Okay, so both directions are trivial if f is simple. So in general, for general f, let's prove it first in this direction. Proof in this direction. Okay, so we know that f is 0 almost everywhere. Let phi be a non-negative simple function less than f. Well, it has to be, this is obvious, phi is 0 almost everywhere, since f is. And it's true, which implies the integral over phi is 0 by the previous comment, which means the sup over all such phi has integral 0, and that is exactly what the integral of f means. Okay, let's prove it in the other direction. Proof in this direction. Okay, so let's look at the set of x on which f of x is strictly positive. This is a union of sets En, where En is defined to be the set of x on which f of x is not just strictly positive, but let's say at least 1 over n. These are all measurable. Okay. What do I want to say? So if f is not 0 almost everywhere, then there exists an n such that the measure of En is positive.
Do you want to say if not f equals 0 almost everywhere?
Yeah, what I mean by this, if not, okay, f equals 0 almost everywhere. If the set on which f doesn't equal 0 does not have measure 0. If this set doesn't have measure 0, well, if all of these had measure 0, measure is accountably additive, so then this set would have measure 0. So if f is not 0 almost everywhere, then one of these has to have positive measure. Everybody see that? Okay. But then the indicator function, so then f is at least 1 over n times the indicator function of En. Well, that's just always true. This is some simple function. So the integral of 1 over n chi En, which will be a lower bound for the supremum over all simple functions less than f. By definition, this is 1 over n times the measure of En, which is non-zero. That's the contrapositive. If f fails to be 0 almost everywhere, then its integral fails to be 0 almost everywhere. Then its integral fails to be 0.
How can we prove it directly without dealing with the contrapositive? Like just start with the integral being 0.
I like this argument. I'm not proving it by contradiction.
No, you're not.
By contrapositive.
Using the inverse.
Yeah. What's the question? I'm sure other people have the same question.
I saw it.
You saw it. Okay. But what was it, just in case?
Oh, it was just the y is up greater than or equal to 1 over I e sort of.
Why is this?
Why is this true? Yes, very good. Very good. Why is this true? En is the set where f is bigger than 1 over n. So it's either bigger than 1 over n or it's 0, and it's always at least 0. Okay? So this is another one of these analysis tricks. It's the same exact idea. Okay. Yeah, maybe there's an intermediate. If I wanted to make this even more kind of obvious, I would do this. And then this. Okay, very good. We have time for, we have time for a little bit more. Okay, let's relax the monotone convergence theorem. I promised you that. Strengthen the monotone convergence theorem by strengthening the theorem. The real monotone convergence theorem, is if fn converge up to f, so fn are my non-negative functions, and they converge up to f not everywhere but almost everywhere, not pointwise, then their integrals converge to the integral of f. Obviously increasing. And the proof is very simple. Let E be the set of x on which fn of x does indeed converge to f of x. Bless you. So the point of this convergence happening almost everywhere is that the measure of the complement is 0, right? So the function f minus f times the indicator function of E, in other words, f times the indicator function of E complement, is 0 almost everywhere. Similarly, fn minus fn e chi of E, which is fn times the indicator of E complement, is 0 almost everywhere. Any multiple of the indicator function of a set of measure 0 is 0 almost everywhere. Okay? What I'm going to do with that is, well, so what does that mean? By our previous theorem, something that's 0 almost everywhere implies the integral of f minus f times this indicator is 0. In other words, the integral of f is equal to, we proved linearity. And similarly, same thing is true for Fn. So the Fn is equal to Fn times chi of e for the same reason. But Fn chi e converges to f chi e everywhere, pointwise. Wherever the original didn't converge, now I killed both of those. In other words, Fn is 0 and f is 0. You see what I'm doing? So now I can apply the old mean value monotone convergence theorem. Integral of Fn chi e converges to the integral of f chi e. But the integral of Fn chi e is the integral of Fn, and the integral of f chi e is the integral of f. George, you don't like something. George, right? Andre, sorry, George, right, Andre.
No, it's as you were writing, like it sort of blurred, so I sort of got lost in the middle.
Sorry. So where did you get lost?
Uh,
Let's do it again. So now I want to know if Fn's converge up to f, not at pointwise, but almost everywhere. So let's look at the set where that convergence fails. That set has measure 0. This difference is f times the indicator function of a set of measure 0. So this is 0 except possibly on this set, but this set has measure 0, so it's 0 almost everywhere. And same thing with Fn minus Fn chi e, because that's the same thing as Fn times chi e complement. So that's 0 almost everywhere. The previous theorem said that if something is 0 almost everywhere, then its integral is 0. And so the integral of f is the integral of f chi e. And the integral of Fn is the integral of Fn chi e. Now look at Fn times chi e. That increases to f times chi e because you're either in e and then you do converge, or you're not in e and then 0 goes to 0. That convergence happens everywhere, pointwise. And so by the old monotone convergence theorem, the integral of Fn chi e is converged to the integral of f chi e, but the integral of f chi e is the integral of f, and the integral of Fn is the integral of Fn. The integral of Fn chi e is the integral of Fn. Question?
So interpreting Fn upper arrow f ae.
Yes.
Does this mean there could be a measure 0 set where Fn plus 1 might not be greater than or equal to Fn? And also there's a measure 0 set where Fn of x doesn't tend to...
No. So I always want, when I write this, I always want the Fn's increasing.
And the ae doesn't say that might fail.
Right. I want Fn's increasing pointwise.
Okay.
Yeah. Let's be a little more careful here. The Fn's are increasing pointwise. It's literally what this is what I want. The Fn's are increasing pointwise, but the set on which their pointwise increasing thing doesn't go to whatever f is supposed to be. F is some other measurable function. Has measure 0. That's what I mean by it. Could you still make it work?
Like you could define
You throw in more sets of measure 0 countably.
Have we said yet that integrating over a set of measure 0 gives you 0?
That was the previous, that integrating over a set of measure 0. So that's a simple function.
Right. Yeah, no, you get 0, but just like it would clean this proof up a lot, right? Could you just like immediately throw away where you don't work?
Essentially, that's what we've
Yeah, that's what we've
done. Yeah. I just wanted to argue why, I wanted to use the previous theorem that tells you why this thing is that and why this thing is that. Which is what you said, you throw away sets of measure 0. But how do you throw away sets of measure 0? You just observe that the difference is a function which is 0 almost everywhere. Same thing.
Why is it pointwise?
Why is this pointwise? So there are x's that are in E. E is the places where this convergence does happen. There are x's that are not in E, in which case this is 0 and this is 0. So whether you're in E or you're not in E, you converge for every single point. Other questions? Okay, we have time for a little bit more. All right, maybe I'll stay. I probably can't prove. Let me try to prove Fatou's lemma. This is really important. Fatou's lemma. So even if you don't have monotonicity, there's a one-sided inequality. This is Fatou. We have a few minutes. So if I have any sequence of non-negative functions, not necessarily monotonic, I guess I do need the word necessarily, not necessarily monotonic, it could be monotonic, then, let me slide this up, the integral of the lim-inf of the fn's is bounded from above by the lim-inf of the integrals of the fn's. Yeah, the proof isn't hard. We can do this. Okay, let's fix a number k. So for any fixed k, let me look at the infimum over n bigger than k of fn. For any j bigger than k, this infimum in particular is at most fj. Let's parse that again. I start with an integer k. I look at the infimum over all n bigger than k of the values of this. Fj, j is bigger than k, so fj is one of these guys. This is an infimum. The infimum is at most one of them. Okay?
So you're going to take the super.
I'm going to take the lim-inf will be. So hence, slide this up. So when I take integrals, so the integral of the infimum over all of these is at most.
This is for like a fixed x?
So
For every
for every x. For every x. Okay. So this is true pointwise. So when I integrate, it's true. And this is true for any k bigger than, for any j bigger than k. This is true for any j bigger than k, for any fixed j. Now, these infimums, pointwise, I will define each of these to be f sub k of x. What happens to these as k increases?
they're increasing.
They increase. Why? It's the infimum over fewer and fewer things. So this is, it's the lim-inf, right? It's an increasing thing. So these increase to capital F of x, which will be, of course, the lim-inf. Monotone convergence. That implies the integral of lim-inf of the fn's is the integral of this big F, which is the limit of the integral of the fk's. But each fk integral is bounded by the integral of the fj's for all j greater than k. And now, and there's a lim here. So this is a lim over j greater than, there's a lim as k goes to infinity, and this is true for all j greater than k, so this is a lim-inf of fk. Maybe I'm skipping a step here. I'm trying to rush. You see what I'm saying? This is a limit as k goes to infinity. For any, let's get this just cleaned up a little. Bless you. Limit as k goes to infinity. Each of the fk's is bounded. Each integral of the fk's is bounded by a limit. Is bounded by an integral of fj for any j greater than k. This is true for all j greater than k, and hence it's true for the smallest one. infimum over j bigger than k of this. And the limit as k goes to infinity, infimum over j greater than k, is, by definition, what a lim inf is. And that's what we wanted to prove. The lim inf, integral of lim inf of the fn's, which is the integral of f, is this limit. It's analysis. It's games in analysis, where you follow these